Good morning, ladies and gentlemen, and welcome to the OEM session by VDMA. My name is Miriam Soleda. I'm responsible for wireless communications in the VDMA, the Mechanical Engineering Industry Association, and I will be here with you during this session and the coming sessions we have planned for today. For this OEM sessions, we have gathered 3 top speakers which are bringing many ideas on technologies, projects, innovations, which are boosting connectivity and which are providing intelligent solutions for industrial applications and mobile machines. You please feel free to ask your questions in your Slido window, which is on your screen. So one of the main technologies we're talking about is machine learning and artificial intelligence. And for this purpose, and to know a little bit more about the use of artificial intelligence, how it can provide and how can optimize your critical processes in your industry, we have here our first guest. I'm very glad to welcome Sascha, Dr. Sascha Lange. Good morning, welcome at the CMM. Hello. I'm going to say some words about you and your life. Dr. Sascha Lange started programming at a very early age, and at the end of 17, he has already founded his first hardware and software company. Mr. Lange has worked for 10 years in academia, where he researched on neuronal networks, reinforcement learning, and autonomous robots. He got his PhD on deep reinforcement learning and won the RoboCup, the Robot Soccer World Championship twice with the Brainstormers Traybots in 2006 and 2007. After leaving academia in 2011, Dr. Sascha founded several tech spin-offs together with the Technical University in Freiburg, and with the goal of transferring the most recent results of this research to the German industry. He's currently CEO at PSIORI, which is a constantly growing international-oriented consulting company with a strong focus on data science, machine, deep learning, artificial intelligence for industrial applications. So please, Dr. Sascha Lange, we're looking forward to hear about your presentation. Please go ahead.
Thank you for the warm welcome and the introduction. So let me just share my slides. Hopefully it's working for you. So my name is Sascha Lange. I just want to add to the introduction that I worked for 10 years with Martin Riedmüller in Germany, and we worked on neural networks, very famous for making reinforcement learning work on real machines that you see in the videos down there. And my personal contribution to the field was pioneering deep reinforcement learning and having the first methods and systems working by 2010. So soon after, the group split, and I decided to found a company in Germany, PSIORI, together with my partner Lars Eickmeyer, here in Freiburg, from the University of Freiburg, moving to the commercial area. And we have also 2 teams in Northern Germany right now. So our focus is, as I already said, on data science, artificial intelligence, machine learning. Basically, we had to plan to bring the things we developed in academia to German industries. And just to show a little bit from our project portfolio, 3 typical projects we did in the company. First one of our earliest projects was building a 6-degree post-estimate vision pipeline that could estimate positions of robots and objects in real time in an experiment for Google DeepMind. We also worked with neural networks and acoustic data for a Daimler, for example, to do quality assurance at the end of the assembly line. And also right now we're working with a Hamburg-based startup on building a lightweight, fully automatic solution for ECG long-term screening. So these are a few of the companies that we've been working with. And this is a team of right now about 40 persons, mainly experts in data science, machine learning, and software developers to build the stuff for our customers. So I brought 2 use cases with me. One that we just finished and commissioned. There the task was to control a shuttle in a mining operation with an artificial intelligence solution. And the other project I would like to highlight today is a pilot project where we're building an autonomous crane in the United States. So first example is about reinforcement learning, and just to show you what reinforcement learning is about. So basically this is a classical benchmark where a machine learning algorithm just needs to learn to control a machine from interaction. And here the task is to move the cart left and right in such a way that the pole is swung up and balanced in the middle of the line there. And as you can see, basically the controller really needs to try out its action and to understand the physics. It actually does know nothing about the process. It only receives a small reward when the task is solved, like here, when the pendulum is upright and the cart is in the middle position. And that's 15 years ago, the system that we've built in academia, and the breakthrough here was that we really came up with reinforcement learning algorithms that were able to learn from real machines without any process information or simulation in real time, and made this feasible for industrial applications. So in PSIORI, one of the reinforcement learning projects we did is with a German car manufacturer, where we learned to control a combustion engine from scratch, just like we learned the pendulum just by interacting with it, and basically achieved within several sessions of interaction with the real combustion engine a quality that could be compared to the solutions that was used in the field. And now coming to this mining operation in Australia, we wanted to bring reinforcement learning also there. Basically, we're talking about this machine here. So you could see the ore that is transported over the line. And here comes up about this distribution machine here. And we can look inside on the right side in the smaller video, where you basically see the ore coming from the conveyor belt. And then it is distributed to one of these outlets here. And there are actually 13 outlets. And when you closely look, you can see that the ore shuttle is moving back and forth at a low speed right now. In reality, it's a lot faster. This was just to be able to film it. And we came in there because this mining operation had problems with overflow and underflow, and basically already had tried several solution providers that couldn't solve all the issues they had successfully with classical methods. So how did we approach the setting? So we came in with our partner Andritz that already has a simulation of this type of machine. You can see this here. And we used that simulation to basically build the AI that should be controlling the system. And we also used this simulation to use reinforcement learning, let the AI interact with the system, and let us train the AI for an initial policy that was already solving the task. One of the optimization goals, so the main optimization goal was to maximize the material throughput. So basically the conveyor belt should run as fast as possible without filling the outlets too much and then having to stop the machine. And the hard feature was that there was needed a skipping feature where basically there must be a small gap in the ore on the shuttle so that the shuttle could travel over a blocked outlet or to a second group of outlets that's a little distance away. And the problem here was that basically the decision when to do this jump to the other group or over a blocked outlet needed to be done like 3 to 4 minutes in advance, because the only way to influence the ore in the shuttle was by not placing ore in the shuttle at all. Then it would travel like 3 to 4 minutes along the shuttle, came in, and then the gap could be used like 3 or 4 minutes later to actually jump over this outlet. Yeah, and So with the initial policy, we then went to the commissioning phase. Unfortunately, at that time, Corona hit. So our project was blocked a little bit because we couldn't travel to Perth. And after it turned out the Corona won't be going away within weeks, we came up with a solution of doing a remote commissioning. So that you can really see here, that was one 4-hour sessions of the 4-week remote commissioning session. We basically went with the AI to the real machine, and then at a setup where we could see upper right image what's happening in the real machine, and also had access to the control system. And that went quite well. And we collected more data there during these first days of the interaction, and fine-tuned the AI afterwards 2 times with this data that was collected on the real machine. So this is one of the exemplary projects we have in industrial automations, process automation with reinforcement learning. Right now, we are working on several other systems. Due to Corona, it's a little bit hard to deliver them because they're also spread over the whole world. But we're working on a thickener and a different mining operation. And we're also working on different processes, the bleacher, chipper, in pulp and paper industries. So the second project I would like to highlight is our autonomous crane pilot project. There the goal is to build an artificial intelligence that's able to support an operator and actually to also autonomously steer a crane of that dimension here. So right now this pilot project runs at a site in the United States, again with our partner Andritz. Here you can see the actual process that should be automatized. So the crane is about 40 meters high and is able to lift a load of wood from this truck with just one grasp. Reasons for the partner and also the customer to actually work here on the automation is first, be able to work with more people or different people that are not that doesn't need that high qualifications that they need right now. And second, they actually aim at optimizing the placement and the speed, how this wood is fed, because there is some optimization potential in the later process by doing that. So when we came here, we first found out that actually these cranes do not have a field bus and do not have the proper hardware to run an artificial intelligence that is able to automate it. So we first built a platform, PACT, that is a mixture from hardware, operating system, and software that has all the connections that are needed here. So it has a field bus, but it can also connect to the cloud and brings the computational power that we need to run neural networks and the artificial intelligence in real time. So additionally, we placed several sensors on the crane, cameras and LiDAR sensors. And you can see here an image that depicts a little bit what the crane is seeing using his LiDARs. So you see on the right, the round thing is basically this wood pile that is around the crane. And additionally, we use a lot. We use a lot of the cameras, so the computer vision, to actually detect parts of the grapple of the crane, and also the loads that needs to be handled. And so here you see the original image of one of the cameras that we placed on the trolley. And on the right, you see what we actually need from this image, basically a representation where's the wood, so the load in this image, and where is the grapple that we need to control. And here you see some examples of the vision pipeline that we built to extract the relevant information in real time. So on the left, you see the trolley camera that actually does grapple tracking and also detects the load. In the middle, you see a headblock tracker that is needed because it can move freely and there's no other sensor to determine like the sway you see in the middle image and also the rotational sway over there. And on the right, you see the side view that we actually use to unload the truck. So In the early layers of this vision pipeline, we completely rely on machine learning and deep neural networks. And we have several types of neural networks here. So we look for key points, like in the image on the left, where we basically want to see interesting points like corners on objects we need to track. We have detectors that just mark objects that are of interest to us with a bounding box. We have simple classifications like that one that just determines by looking at the image whether the grapple is open or closed or whether it's loaded or empty. And also we rely a lot on semantic segmentation, that's the image on the right, where the neural network really understands where in the image or which pixel in the image belongs to which class. Namely here, there's wood in the background and red is the grapple that has been marked by the neural network. So when you do things like these, you always need training data. So that is basically, we need a lot of images to be able to train our neural networks. And we need good labels or annotations on the images that we can use in supervised learning. So when we came to this project, the question was like, how can we create this? Because the off-the-shelf pre-trained solutions won't work in this specific domain. So what we did is we built a platform that allowed us to connect the crane to the cloud. So on the left, you see the crane with its edge devices, the PLC, but also some classical computers that do the camera processing, run the neural network, and basically have the capacity to do the processing. We use some cellular connection to the cloud and send the data there that we needed for the training. And this is quite tricky because we produce about gigabytes per second on the crane just from the different cameras and leaders. And obviously this cannot be transferred and also not stored. So we have a smart filtering algorithm on the crane that just looks for data that is interesting to us, uploads it in the background as fast as possible using the edge connection, and then it's in the cloud. And here in the cloud, we also have some UI to see the data and interact with it, and also browse the log files. And of course, our developers are able to work with this data to train the models. Here you see the data dashboards that we've developed as front end. Here you see a live stream from the crane, and also all the images that we collect and come in over time. And then additionally for our developers, we have an interface that actually has a semantic indexing of these images. So the images would be just dump data. And when it comes in, we connect it to all the log files that we have from running the AI, and also the information we grab from the PLC on the crane, and basically index the training data with these meta information. So what you see here is right now a developer asking for specific images of a specific day, of a specific camera in the system. And you see this can be interactively done, and the images are displayed immediately. And we can also ask for specific data by providing some bounds on, for example, here is the gantry position. So basically we're asking for specific directions that the crane looked, and the system will output all the data with the meta information. So these data, when selected by a developer, can be exposed to the public. And also we send them to a sister company, Quality Match, that provides an annotation service, a crowd annotation service. And so by selecting the images that we want to have in our training set and sending them, we enable them to send these images to their crowd that then does the annotations in the images, marking like hundreds of images, all the interesting objects, or painting a polygon around the grapple for us to be used in training data. So this comes in within a few hours, like 1 to 2 days, for a number of 500 to 10,000 images, and directly goes back to our cloud architecture, and then is again connected with the meta information about the images. And this then is used to train the neural networks we use in the system. So another thing I would like to show you is how we approach the problem of sway control, because basically the crane is free swinging on the cables, and there is no encoder telling us like how it's positioned in the world. Now, we needed to get this information and also get some control to A, prevent it from swaying when we start driving, but B, also to reduce the sway that is introduced by interference like wind or interacting with the wood pile or the load on the truck. So basically, we first did a small lab experiment where we just built a pendulum and placed a wireless custom IMU at the top of this pendulum. So what you see it down there, it's just battery-driven wireless and communicates 6 degrees of freedom back to the AI. At the topmost, you see the control without any sway control and any dampening, so it's just swinging a lot. In the middle, you see a control that actually does a prevention of the sway when we start driving. So see it here, that it immediately cancels it after its acceleration. And at the bottom, you see an image you saw in video of the active and the passive damping together. And then after developing this in the lab, we brought this to the wheel crane. So you see it here, an example on the wheel crane. So here we ask the driver to just introduce a lot of sway into the grapple that we later could cancel. And then we switched the sway control on and told the driver to just move the crane to the left without caring for the sway anymore. And what could you see here is that the sway control quickly removes all the sway from the large grapple. So this was done using classical methods. So here right now, there was no machine learning involved, just some data science and developing these control laws. But this is also an opportunity for reinforcement learning that we're working on right now, because for the optimal operation and the process later on, it's not just important to reduce the sway, but to also move as quickly as possible. So reducing the sway always makes the crane a little bit slower and also a little bit imprecise, because it won't stop at the exact position where we want it to stop, because it's still occupied with canceling the sway. And this is an opportunity for the reinforcement learning method to just come up with policies that stop at the exact position with all the sway canceled in an optimal fashion. So last thing I would like to highlight from this project is that also Corona happened. And I told you that we had a cellular connection to send data to the cloud. Unfortunately, due to Corona, we weren't able to travel there anymore. And we had to come up with a solution in the summer, like how could we continue the project in the development phase while not being at the crane. And so we removed the cellular connection and got a cable connection and built the infrastructure and also the software to be able to remotely control the crane from Germany with seeing the state that you see in the middle, representation of the crane state, and also getting some image information from the real process with less than a second delay, so that it was basically possible to operate it from here. And so that's the timeline of the pilot project that we're looking right now. So if Corona wouldn't have happened, we would be finished by now. So we are a little bit late, but working on this timeline again now that we can remotely work. Right now, we're working on a fully autonomous truck unloading. That's the next in our roadmap. And we plan to commission the autonomy functions as soon as Corona allows, hopefully in the second or third quarter of the next year. And we also want 2 other projects here in Europe, where we will deliver the first portal crane that operates fully autonomously in a woodyard in 2022. Yeah, that's everything I wanted to talk about today. So last thing is I can do is thank you for your attention and also for my team that did all the work. And when you found this interesting, I would like to invite you to come to Freiburg, and probably that's possible even due to Corona. There we have a smaller crane that basically has the same functionality as the large crane that we're working on in the United States. Okay, thank you very much.
Thank you very much, Sascha Lange, CEO at PSIORI. We have a couple of minutes left. May I ask you some question? And it was,
yeah, of course.
We have been these impressive examples of applications for the crane and for cranes and mining operation. Are you planning to expand to other industry markets or fields with these solutions? Because I think they have such a potential.
Yeah, so basically with reinforcement learning and deep learning neural networks, we're working specifically in the medical field already with other partners. And in this industrial fields, it was just a small subset of the projects we do. Usually we are open to do consulting projects and in control problems that are not easily solved with standard methods. And also we're working closely together with our partner Andritz on different processes in the pulp and paper industry.
Thank you very much. So we don't have any time left. So we have to say goodbye to you. We thank you very much for your impressive presentation. Ladies and gentlemen, if you have any question, please feel free to contact Dr. Sascha Lange. I'm sure he will be happy to answer you and to provide enough information regarding machine learning, artificial intelligence, and these exciting topics. So we're moving on, ladies and gentlemen. We had Dr. Sascha Lange mit PSIORI, von PSIORI, and with the use of industrial artificial intelligence and deep learning industrial applications. If you have any question, please use your Slido window, which is on your screen, and write your questions which you may have for our speakers. We are in the OEM session by VDMA. My name is Miriam Salina, and we're moving on to a second topic, which is quite interesting and which is affecting all the stakeholders in the value chain, which is digitization and data exchange between machines. And the point is that for many users of mobile machines, they're confronted with solution applications which may be incompatible, which are isolated, and which is brings some difficulties in the interpretation of data content. To this point, to this issue, we are very glad to have here our next guest. He's Dr. Darius Soßdorf. Darius Soßdorf is, hello and welcome to the CMM, Mr. Soßdorf.
Yes, hello, Salera. Thank you very much.
Mr. Soßdorf, we cannot hear you. Can you please unmute your microphone?
Yes, can you hear me now better?
It's perfect. Thank you. Thank you very much.
Thank you very much.
I'm going to say some words about your role, your work in, what you are doing at the VDMA and the Machines in Construction. Dr. Darius Soßdorf is General Manager for Machines in Construction, MIC 4.0, and General Manager of Research Association for Construction, Equipment and Plant Engineering at the VDMA, the Mechanical Engineering Industry Association. Mr. Soßdorf studied chemistry and managed laboratories within the industry. In 2002, he joined the VDMA to establish the EU Chemicals Policy Reach in mechanical engineering. In 2015, he changed to construction machinery, where he's General Manager of Research since 2017 and General Manager of Machines in Construction, MIC 4.0 since 2019. So, Mr. Soßdorf, I'm very glad to hear you and to hear your presentation. It's all yours.
Yeah, okay.
Thank you.
Thank you very much for the introduction. Yes, as you may hear, General Manager MIC 4.0. What are we doing in MIC, in Machines in Construction 4.0? Everyone is talking about digitization. And the question is, what is digitization? Digitization is not only the transfer of data, it's also the understanding and the common interpretation of data independent of the manufacturer and independent on the machine. Today we have the problem that every machine manufacturer gives his own solution. This is okay. So the problem is only that you have different solutions and the user of the machine a construction company has the problem that every machine they have in their system, this machine gives an own solution for their software. And the problem is the understanding, the common understanding of the incoming data. And the main question at the beginning is, in which condition is a machine when a machine is sending the data I am on? This is the starting point for MIG 4.0. And let me please share my desk with you, and I will give you a short presentation concerning what we are doing in MIG 4.0. So I will have a look that you can see my screen. I hope you can see my screen. Machines in Construction 4.0. This presentation is worked out by a little bit from myself, but most of the slides are coming from Thomas Unterdorfer, one of our member, Liebherberg Bischofshofen, because he's an expert on digitization in Bischofshofen. Yeah, development and founding. Fields of work for digitization, which we have identified in 2017. So we have the question, what data and in which form does the respective actor in the value chain need? Definition of necessary interfaces. Everyone is speaking about interfaces, but the question is, what is an interface and what is a common defined interface for interacting with data between machine, cloud, server, user, and so on. And we have an initial workshop on which an end user, a construction manufacturer says, you are building very good machines, but I will tell you how you can build these machines in a better way. Absolutely bad information. And we ask, what do you need? And this is the start, that we sit together on a table and the user of the machine said to the manufacturer, I need this and this and this in this and this way. So we found the Machines in Construction Working Group on 8 April of 2019 in the frame of Bauma 19. Currently, we have 88 members from 4 European countries, and we are become much more larger in the future, so I hope. 65 companies from VDMA, it's the manufacturer side, the OEM manufacturer, 19 companies from the construction industry and other economics, like positioning system, like software and so on. And also we have questions, we have to answer the question, we have to research some new information. We have 4 universities. MIG 4.0 is organized as a working group in cooperation with the Hauptverband der deutschen Bauindustrie, HDB, main association of the German construction industry. It's not only a VDMA working group, it's a joint working group in cooperation with, and we both, VDMA and HDB, are going under the label MIG 4.0. The executive board of MIG 4.0 is currently made of the managers from Bauer Maschinen, from Bomag, HDB, Hermann Paus, Leonhard Weiss is a construction equipment company, Liebherr MTech, VDMA, and Wacker Neuson. You can see from the original equipment manufacturer, we have some main global player inside, and they are giving the course on which we want to come up. Main topics, processing on the topics, we are based on the ISO standard 15143-3, because it's a current used ISO standard, but unfortunately, no one is using the standard. And we ask the question, why is no one using the standard? We are looking to machine-to-machine communication, of course. We are looking from machine to BIM communication, of course. Data rights is one of the questions. If you're dealing with data, you have to ask the question, how can you use the data, when we can use the data, from which we can use data, and how we have to handle some confidentialities concerning data. We're also dealing with attachments. An attachment is not, in the most of the cases, not a machine, it's an attachment on the carrier machine. And we also ask questions and try to find solutions for the communication human-machine interface. How kind of interface can make the use of the machine easier, better for the user? And our slogan is doing instead of talking. Why this slogan? Okay, we consider that everyone is speaking, is talking about digitization in workshops, in seminars, in what else. And we in MIG 4.0, we said, okay, let us talking about digitization, but also let us find common solutions for the question which are upcoming with digitization. And so we have our machine data working cycle. It's the main working cycle of digitization of MIG 4.0, because the machines are giving us the data which we want to transfer to the user, to the software, to what else. The short term of the goal is that we agree to a uniform understanding of the data supplied by the machines across manufacturer. As I said to you, my machine is on, your machine is on, but is this machine from my side and the machine from your side in the same condition? Most of the cases, the machines are not in the same condition. And in the first step, we have focused on machine condition data, which is from the ISO 15143-3, because these 20 data in this ISO standard is present, is accepted, and we want to have a look first of these 20 data. Because they describe the machine usage, the condition data. In the second step, the user said we need machine working data, because concerning BIM, concerning quality and so on, we need the kind of data which describes our working process of the machine. And as a result of this, the description of the results and the quality of the working process of the machine. Wherever possible, we are based on existing standards. We do not change standards or common approaches in MIG 4.0. No, we use given standards. And in the case if we do not have given standards, we try to come up with new standards in the EN standardization or the ISO standardization. Here you can see as an exemplary extract one of the first results which we have to finalize end 2020. And according to the ISO only earth-moving machines, we also have a look on these data concerning cranes, special foundation equipment, road construction. Not all of the data which can be used and which is given in these ISO standard for earth-moving machines, you can use for cranes or special foundation. But we look what kind of data from this earth-moving machinery standard can we also use. And this we put together in a matrix. And then you can see in some additional words, we come to a common understanding. And as I said at the beginning, the common understanding of the question, is my earth-moving machinery on or off? In which condition is my earth-moving machinery on and off? We come together with all original manufacturers to the common understanding if the crankshaft is rotated. This is only the case if you have a combustion engine. Of course, electricity we have to look later on. But if you have a combustion engine and if the crankshaft is rotated, then the machine condition is on. For all manufacturers, the same understanding on if the crankshaft is rotates. Now you can ask, what's so difficult to come to this common solution? Yeah, the difficulty is that all manufacturers has to accept this common understanding and have to give this common understanding to the user of the machines. The next step, we come to the definition of the machine working data, which the users of the data, the construction companies, need to give an overview of their work process for BIM, for example, for some other information concerning the quality, and well advanced in special foundation engineering, this second step, because they have identified relevant procedures. And these relevant procedures like Kelly drilling, like other procedures, we have to look what kind of working data we have in this special procedures in the construction work, on the work site, on the job site. The next important step is attachments. We have an EN standard 474-5, and they are definitions concerning base machine, equipment, and so on. But the question is, where is the interface between base and equipment, base machine and equipment? And so in MIG 4.0, we make a clear common understanding also over all participant manufacturers the equipment and the attachment has this interface. You can have a look on these slides later on because I give you these slides and you can look every detail in the slides. If I'm a little bit fast currently at the presentation, depends on time, that's clear. You will receive this presentation and you can have a look by your own. Interface for bucket kinematics cuts straight through the bolt axis of the bucket kinematic of the arm. This is a definition of data interface of equipment and attachment, which we now have a common understanding in MIG 4.0. The same is like this one, another kind of attachment. As you may know, you do not only have one or two attachments. It depends on the question, what do you want to do with your machine? And the question is, what kind of attachment do I need? And on this slide, you can see how many possibilities of changes you can have. More complex combinations will be examined at later time. You can have a quick change adapter, you can have a tilt rotator, a quick adapter change, a tool. And these attachments have to have a communication between itself and between the carrier machine, between the equipment. And the question is, where is the interface? At the next step, it was terminated for November, but because of the Corona pandemic, we cannot have our Plugfest. So we have to put the Plugfest into January. We want to show that 3, 4, 5 original manufacturers of the machine and 3, 4, 5 manufacturers of attachments come together and have a Plugfest. The aim of this Plugfest is that each participant uses a laptop to simulate an attachment or an excavator, and then the user can see, despite of which kind of attachment or which kind of excavator I use, I will all times receive the same information. It's absolutely independent from the manufacturer of the excavator and from the manufacturer of the attachment. This is what we do not have currently. And this is what we want to show it's possible and what we want to achieve in MIG 4.0, that you do not have every manufacturer with his own solution. You have a common solution, absolutely advantage for the users of machines and attachments. On this slide, you can see what we are doing in the field of system architecture. Please respect only the red labeled interfaces. So in MIG 4.0, we have a look on the cloud to server system architecture, because this is given in the ISO standard, but it's also not defined and it's not a common understanding over all manufacturers and all users. So we also want to come to a common interface concerning cloud to server based on the ISO standard. We also want to come to a common interface from machine to attachment. This is what I show what we want to achieve with the Plugfest in January. And as I said, we want to come up with a common interface, not one interface for all machines, but a better interface on which you can see the same symbols, despite on which kind of machine you use. It depends on the function of a machine. Going forward, going backward, going left, going right can be the same symbol of the machine, because we also have an ISO standard for symbolic, ISO 7000. The question is, why do the manufacturer use so many different symbols for the same function or the same condition? And this is also one thing what we want to have a solution in MIG 4.0, a common understanding for a human-machine interface for better using on the side of the users of the machine, for better understanding, for better learning, and based on the ISO 7000 standard for symbolics. We also have a working cycle on data rights. As I said, if you are dealing or handling with data, you have to ask some questions. What is about the data? Where is the data coming from? What can I do with the data? Who else can also use the data? In which way? A lot of questions. And we're creating also a common understanding of data generation and data use among among all members. Develop a legal regulatory structure, and also we bases the entire work of the current national and European data legislation. We do not want to come up with new legislation or new standards. We want to have a look what is currently actually on the market, and we have a look what can we use for MIC 4.0, for our aspects, for our questions. And in the case if we have no answers, we have to come up with develop new and legal regulatory structures for MIC 4.0. This is what I said about human-machine interface. This is an example, for example, for a wheel loader. Here you can see some symbolic, some symbols from the ISO 7000 standard. And if you use lights or a high flow or what else, why do not the manufacturers can use all the same symbols from the ISO 7000 standard? And this is what we have to agree to come up in MIC 4.0 human-machine interface. I want to give you the information that we also have on the homepage. On the homepage, you can also receive some actual information. You can receive some fundamental information, how to become a member. You can also see the working cycle structure and so on. So please have a look on this homepage. Please pick up some information. And in the case, if you do not found all information, so please do not hesitate to contact us. This is the contact to the office. It's myself, it's my colleague, the assistant in the office, Verena Schmidt. And in this case, at this point, I want to say once again, many thanks to my colleague from Liebherr-Werk Bischofshofen, Thomas Unterdorfer, because he's absolutely deep in the work of MIC 4.0. So I hope I can show you what we are doing in MIC 4.0. We want to bring together the manufacturer on the one side and the users of the machine on the other side. And we want to have at the end a solution which is a common understanding of what we are talking about. Is my machine on, yes or no? Is the other machine from the other manufacturer in the same condition if it says on or off? And this is what we want to achieve, what we want to come to a common position in MIC 4.0. So I will say thank you for your attention, and I'm absolutely open for questions from your side. Thank you.
Thank you very much, Mr. Soßdorf. It was a quite comprehensive presentation of MIC 4.0. And I have a question here for you, and it has to do what happens with the requirements and the wishes of a certain customer when a company wants to be member of MIC 4.0, how they're going to be considered.
Yeah, the question is very easy. Please have a look on our website, see our structure of the working groups, see our working cycles, system architecture, machine data, data rights, and so on. And please ask yourself, what is your job in the question of digitization of construction equipment? And if you say, I have to do because my customer is asking for this and this and this, then please get with me in contact and we try to find a solution that you become a member of MIC 4.0. Doing instead of talking. It's the same like standardization. You can only put your interests on the table if you become a member and work with us together. If not, you have to receive what we develop at the end of the process.
Yeah, thank you. Thank you very much. Quite clear. I have another question. It has to do with your demonstration Blackfest, which you said you had to postpone due to the corona pandemic. Do you have a date for it, or what is the schedule for it? Do you have a current schedule for it?
Yeah, if it is possible that we meet physical, so we come together and make our Blackfest. The work in front of the Blackfest is done, we are finished and we can start. The problem only is that the data transfer over the internet is not fast enough. Mm-hmm. You cannot very good transfer CAN bus data about the internet. This is what the experts said to me. So that we have to meet in physical with a laptop, with a USB stick, with 2 laptops, that the transfer of the data can be given in a faster way.
Mm-hmm. Thank you very much.
So if we can meet physically, then we start with the first Plugfest.
So we have to wait a little bit until we know what's coming next. Thank you very much. Darius Soßdorf, General Manager, Machines and Constructions, MIC 4.0, and General Manager of the Research Association for Construction, Equipment and Plant Engineering at the VDMA. We're here. Please remember that you are going to have access on demand to all the videos and presentations which are being presented here. So in case you're missing some kind of information, don't worry, you will have the chance to get it. And if you have any questions for our next or guest, please use your Slido window in your screen. We're moving to another tema, to another topic, which is robotics in the industrial field. And I'm very glad to present our next guest, because he says, he claims that smart factories need smarter people, and that operators have to become creators, which is very interesting. And there is no need to choose between robots, machines, and people, but they are both. They can come together, and they should work together. So our next guest, I'm very pleased to have here, is Bruno Adam. Bruno Adam, I'm going to introduce him, is General Manager, Mobile Robots Europe at Onrom Industrial Automation. Welcome at CMM, Mr. Adam. I'm going to say some words about you and your work at Onrom, and then you will be able to present your presentation. Mr. Bruno Adam is General Manager at Mobile Robots Europe at Onrom since the commercial... Okay. I'm going to say some words to Mr. Bruno. Since the commercial launch of Onrom Mobile's robots in Europe in 2013, Bruno Adam manages a team in charge of identifying the main markets and applications that require flexible and adaptive transport and convenience. The unit is supported by a team of applications and software engineering to deploy the technology in the manufacturing industry in Europe. Mr. Bruno Adam regularly represents Onrom as a keynote speaker at various industry summits and seminars. So thank you very much for being there. You just had to change your camera. Welcome. We're very looking forward to your presentation and your claim to say that we don't have to choose between mobiles, machines and people, but they have to come together, and smart factories need smarter people. Please go ahead. Oh, Mr. Adam, you're mute. Your microphone is mute. We cannot hear you. We still cannot hear you. Your microphone is mute. Yes.
Can you hear me now?
Yeah, yes, perfect.
Okay.
But we cannot see
Sorry
you.
about it.
You have to come, yeah, so. Thank you.
Okay, because I have 2 cameras. Sorry about the problem. So thank you very much for the introduction, and thank you for attending this presentation about connected mobile machines. And yes, as you said, I'm in charge of the mobile robot business for Onrom in Europe. I've been in the robot business for many years. Let me start a little bit this presentation. Yes, just to introduce a little bit myself. So we have a nice plant here in France. So I'm based in Annecy in France, so close to Switzerland, in a nice place where we have a nice showroom and facility to present mobile robot demo, do proof of concept, feasibility studies, and presentation to our customers. So let me start this presentation. Something I like at Omron is the motto that was developed by our founder: at work for a better life for all, a better world for all. This is very important for me. This is my main direction for the developments. So let's start, and also the philosophy. I'm trying to start every day, my day with how my business could create value for the society, and how should we make innovations. So I believe that mobile robotics is a very good vector in that way, and it's what I'm going to present today. So yes, if you look at the slide here, we have so many different, so many technology that we call Industry 4.0, and that can bring a lot of value to the society. And we have big robots, we have mobile robots, we have fixed robots, we have vision system, motion control, PLC. So a lot of automation technology that can bring a lot of value to society. So let's discuss that today. So over my many years in the automation business, I spent quite some time in doing some improvement. And the biggest difference I can see between when I started my career in the 90s and what I'm doing now is in the past we used to do a mass market production, so we really had this made from stock concept that is made for me today. So it's a very significant change. So we don't have this in a lot of industry. I mean, in automotive industry, in the food and commodity, but even in the automotive industry, we can see a lot of change, and people want to be able to customize their product and have exactly what they want, what they like, when they want. And this is making a quite significant difference in the business organization. So we need much more flexibility. We need the possibility to swap from different type of manufacturing. And this is obviously creating some significant change. So we have to rethink completely the manufacturing. So the good thing is we have plenty of tools for doing that. So we have obviously the autonomous mobile robots we are going to discuss today. And we also have the system integration, the Internet of Things. So we have cybersecurity, cloud computing, additive manufacturing, augmented reality, big data. So a lot of tools that we can use together to try to find the best solution for our customers. Obviously, it's always a trade-off, so we have to basically define some priority, define some importances for the different technology to do some achievements. But I like to myself to play with all this technology to try to address this new way of thinking. So again, in the past, in the year 90s, we were mainly talking about automation for mass manufacturing that came with the electrification. So later on, we were using automation, using computer integrated, so that changed quite a lot. And then the information arrived, and we had consumer integrated manufacturing. And then to come up to personalized manufacturing, it's what we are doing today with autonomous and intelligent factory. So this was to move from large mass production for push model, and then we are trying to move to a different type of organization. So when we moved from electrification to automation, we were already changing from large to a mega factory and using computer integrated. Then we tried to optimize a little bit better the manufacturing and use a more medium-sized organization. We were still in push flow model, but we were already more responsible, more flexible, and closer to our customers. And now we are coming to a new model that is much more, much closer to customer, and what we call on demand, and with obviously a lot of more responsibility and to arrive to the flexible and reconfigurable manufacturing. This is what we call near manufacturing, so very close to customer. Obviously, we cannot imagine to have some very customized manufacturing. So if my kid wants to order a new pair of shoes on the internet, it's difficult to imagine that this pair of shoes will be made somewhere in Asia and then transport to Europe. These people cannot wait for 4 weeks or even 4 months to get the goods. So we need to build that much closer to the end users, to the customers. So we are decreasing the volume, and we are increasing the mix of the manufacturing. So this gives us to a kind of a level of scalability also on the manufacturing tool that we need to achieve. We have also to be able to change and to have the ability to change in a very quick way. So if we think about scalability, so we have at the machine level, so we have to have the full scalability for the entire manufacturing tool. So we have to have changeover ability in the machine and cell, and we have to be configurable from cell to line, and then the entire factory needs flexibility, and the enterprise needs that autonomy. So this is what we call transform, transfer, and transport. So these are the main points. And so for the transform aspect, so we have been on that for a long time, and then now the fixed robot market is getting more or less a commodity market. I mean, when a new manufacturing plant is designed, we know that they need to use some fixed robots for doing this assembly, for doing this inspection, for doing this packaging line. For the transfer, it's already a little bit more difficult and not very common to everybody to organize the transfer in the right way. So to organize the manufacturing flow in the right way, and the transportation is very new. So I saw so many customers saying that, okay, my process are getting more and more sophisticated. I use motion control, I use robots for my process, everything is automatized, but I pay more and more people to push some small trolleys, to push a small, lots of parts from process A to process B. So this is what we need, transportation to transcend the enterprise. So this is basically our vision of the development. So the main goal is to basically bring agility, but for that we need to have a global view on the development. So we need to break the barriers between the equipment and the people, and we need flexible and reconfigurable flow for the material, obviously. So, and that again at the global level. So we need to have a global view of the entire enterprise. And reach the good level of reliability and efficiency. So when we talk about global view, we need to talk about people. So obviously the people are the most important of every manufacturing plant, and they need to be informed the right way and work in safe and secure configuration. For the process, it needs to be digital and lean, but as we discussed before, the process are already quite well organized and very well optimized and automatized. And then for the entire manufacturing, so we bring what we need, the intelligent and autonomous factory. So based on that, so what's next? So what can we bring next with connected mobile machines? So we talked about the process, we talked about the equipment, we talked about the people, and all that needs to be integrated, intelligent, and interactive. So this is a big picture of all the project, all the plan development. We need to have this magic triangle between the process, the equipment, and the people. So regarding interaction, so we need to have real-time process information feedbacks, so for the integrated, so we have integrated plans, so we have very good data transfer and good transportation between the different equipments, and everything needs to be intelligent, autonomous, and collaborative. So it's basically the different pillars that we have to improve over the time if we want to reach the excellence and the transcendence as I was presented before. Also, we need to have the right quality process in place and the right efficiency of the entire equipment. And this is obviously, when we talk about new technology, it's most of the time quite challenging to achieve that. So let's take some examples. So this was a little bit more or less the theory. Now, if we take the equipment, here on this picture, you have an example of a practical example where we need on the left side, I don't know if you see my mouse, but on the left side, we need to transport the raw materials from the stock to the packaging stuff. So basically to unpack the raw material, and we can use robot to unpack the raw materials. And then we can use some more mobile robots to bring the raw materials to the transforms. To the transform location where we have a process to transform the raw materials. So this is on the right side, right top. And then the goods needs to be moved from this transformation process to the repackaging, and then the primary and the secondary packaging. And then we need to palletize that and bring that back either on the finished goods storage system or directly to the end users or to the market. So that's typically what we need to do on every manufacturing plant. So if we want to get also the level of flexibility that we need to achieve for that, we cannot work anymore in a sequential line that we used to use in the past. Now we have to desequentialize the manufacturing and define it in multiple cells. Then obviously we need to bring the goods to the right cells at the right time. So it's where we need this connected mobile device to bring the right good at the right location at the right time. And the good way for doing that is to have something that is completely autonomous. And we want to be able to use that as a taxi. So when the machine has some goods to bring, then it can ask the closest robot to bring that to the right destination. And then the navigation system should be in charge of taking care of all the navigation, and exactly like on the taxi, where the taxi is finding for you the best way to go to your destination. So let's take a couple of examples of a real fleet of robots that we have deployed at customers to achieve that. So the first one is basically a demonstration of an example. So unfortunately, we are not able to show the real line. So it's just a concept line that was developed in our lab, and where we can see the different step of the packaging. So this is a very short video that explains a little bit how we address this different topic that we already discussed before.
Utilizing collaborative robots, high-speed autonomous robot deliveries with embedded track and trace technology. Let's start off the sequence at the centralized deep palletization station. The operator scans the barcode on the packing slip for each new pallet that comes in. This will trigger a new job sequence as the MES sends the mobile robot to the respective depalletization station. At the station, the Vision integrated cobot scans the barcode on the carton box before loading it onto the mobile robot. The MES system will then send the AIV to the available packaging station. At the packaging station, a zero-weight conveyor receives the new carton and releases the empty carton back on the mobile robot. This is achieved in one seamless motion and with no waiting time for the mobile robot. The mobile robot then takes the empty carton off to a centralized compacting station. Back at the zero-weight conveyor, the collaborative robot scans the carton ID before picking it up. The carton is brought to the unboxing mechanism to have it sliced open. After that, the contents of the carton are emptied onto the hopper, which will be the in-feed to the tray filling station. At the same time, the empty carton gets placed back onto the zero-weight conveyor for the next mobile robot to pick up. From the hopper, the items travel along the conveyor towards the tray filling station. At the tray filling station, a Delta robot packs the items onto the trays. Once the trays are filled, they pass through a camera where the barcode on the tray is read, and the tray gets packed into the box. All of the previously scanned data for that item is compiled into a data matrix code and printed on the box. This code can be scanned at any time to get complete, traceable information of the finished product. The complete line data is captured and sent to a database-enabled controller. From here, information such as the OEE, throughput, and other useful data is visualized on a central dashboard. This provides for easy line or plant monitoring at one glance. The top portion displays the IoT line data, while the bottom half shows the traceability data. We hope you enjoyed our demonstration. Thank you.
Okay, thank you for basically attending this presentation, this video. Let's take, I hope we have time to take a second example for a fleet of 9 mobile robots that basically are working today at Dvola in Denmark to manufacture and produce some tap for kitchen, bathroom, and so on. A very high level of quality. So let's have a very quick look at what was done at Dvola.
Phase 1. And we chose only because they were the ones that had the ability to have a fleet control where they can control more robots in the same facility. This is by far the most advanced solution we've seen yet. So the robots take empty totes out to the assembly area. Then the workers scan the tote to see what's going to be produced. They produce it, and then the mobile robots picks up the finished goods in the totes and put them back into the warehouse. We are very much focusing on being able to react to different demands in the market and make a high-end, high-quality product. So everything assembly is built by hand, but the moving around is now done by robots. By moving some of the heavy stuff away from the workers, it's also for them a better workday. The main advantage with mobile robots is the ability to change things around very quickly. Instead of, for example, putting a conveyor system, with mobile robots, you can easily make a new way around and then change the layout of the factory if you want. We're now starting off with phase 1 with this line of mobile robots, and we have a phase 2 and 3 where we are even more focusing on the rest of the factory of getting all items moving, actually. So hopefully online will be a big part of that in the future as well, and we see big opportunities in getting more flow into our factory.
Okay, so this is a very good other example that also I like because it's a good transition to the the next step, which is the human factor that we need to address. So the smart factory needs smarter people. So it's basically what was explained by this Vola COO just before, where people can pay more attention to be creative and to to do the smart job when the robot is doing the boring job, just doing transportation with very low value added. Successful factory of the future are those who turn their operator into creators. So again, this is a very important point, and it works in both ways. So I mean that it's because we use modern equipments and new technology that we free up sometimes for operator to be creator instead of just operators. So one important thing is let's think about man and machine rather than man or machine. So which is again a very important aspect on this development that we are doing and that we need to do in a very global way. Well, something very important, it's a journey. I'm not saying that this is very easy to do. It can be done just in a few hours and can be very easy deployed. Again, we need to have a global approach. We need to work and have the real analysis of your needs together before starting any deployment and even before defining the right system architecture and the right technology for that. So again, it's a journey, and I hope we will be able to have this journey together. So let's have a little bit of time for a question and answer. I don't know if there is any questions from your side. Again, thank you very much for your attention.
Thank you very much, Bruno Adam, General Manager, Mobile Robots Europe at Omron Industrial Automation. It was very impressive, your presentation and your videos with these mobile robots. And one question is, what criteria, what has to be considered when I decide to introduce or to get some mobile robots for my production, for my industry? What should I look for?
So thank you for this very good question. So there would be a lot to say about that. The first aspect is obviously the payload that you need to transport. So is it something very heavy and that we need to transport by big robots, probably at a smaller, at lower speed, and obviously associated with the weight is the throughput that you need to have. So at this level, we need to always find the right trade-off. So either we want to have a very big throughput with limited flexibility, and then we will transport pallets, for example, up to 1.5 tons, or maybe we want to be much more flexible and be able to transport some much lower lots, so a small box, or maybe a KLT tote of 10 kilos or 50 kilos or 100 kilos, then we will use a different robot that will be probably faster, but the transportation time for the complete system handling will be at the end longer, obviously. So again, it's always a trade-off between flexibility and productivity. So speed, weight, and throughputs are the main drivers for that. But also the environment is very important. So if you have a very well-organized environment with some room, obviously it will be much easier for mobile robot fleet to evolve in that. If you have a very crowded environment, like in a clean room environment for microelectronics, for example, where the square meter is very expensive, so we need to optimize as much as we can the size and the room that we are using. Then we have a lot of machines for a small environment, and the mobile robots needs to have a very high level of agility to run around the machines, but also run around people. So this brings us to one more criteria is what we call the dynamic environment. So either you have a very static environment, so it means that the environment is not changing over the time. And this is obviously much easier to address, but we need to be able also to propose some solution for what we call dynamic environment, where we have a lot of people moving around, where the machines are very changeable in terms of form factor or in terms of dimensions, and maybe the factory needs to store some equipment in some locations, and the robot will have to adapt to that. So these are all some criteria that we need to address and that we are addressing with a different type of robots we propose. But again, it's always a trade-off. So if you want to have a very high flexible environment, if you want to make your fleet of mobile robots running in a very dynamic environment with a very high level of flexibility, you won't be able to achieve extremely high throughputs, obviously. So it's, again, we have to keep in mind that this is always a question of trade-off.
For your
I
answer.
hope I answered the question.
And one more question. In very dynamically environments, how do you assure that the mobile machine has a fast real-time reaction time to elude collisions or some other kind of, how do you guarantee this real-time activity of the
well,
mobile?
Yes, obviously there are some limitations to that. So if it's very dynamic, then the robot will need more time to navigate in that, because obviously what we want is not to have any contacts between the machine and the environment. So if we talk about dynamic environment with some pallets, for example, that can move from location to location, that's much easier to address than if the dynamic environment is mainly due to a lot of people moving around. Obviously, when we talk about people and what we call dynamic obstacles, that's much more difficult to address. So what looks very easy and obvious for humans, it's not so obvious for mobile robots. So, for example, our we are always trying to involve the behavior of our mobile robot based on the environment. So in the past, for example, the mobile robots were detecting some what we call the dynamic obstacles, so some operators. And when they see an obstacle, the mobile robot can decide to pass this obstacle on the right, for example. But the right is the direction of traveling, can be the direction of traveling for the operator. And then instead of trying to avoid the operator, it creates a kind of competition between the mobile robot and the operator. And obviously this is not efficient for the throughput, and the mobile robot is wasting a lot of time trying to avoid this dynamic obstacle. Mm-hmm. Now, something we introduced a couple of years ago, it's what we call the dynamic obstacle management. And the robot has the ability to detect in which direction the dynamic obstacle is going. So and then the robot takes the decision to pass it on the back instead of passing this obstacle on the front. Obviously, this seems very obvious for human. It's not for a mobile robot. So it's very complicated to have the right algorithm in place that can address this type of request at any time in any configuration.
Mm-hmm. Thank you. Thank you very much for an explanation, and thank you very much for being here with us at the CMM. Bruno Adam, General Manager, Mobile Robots Europe at Omron Industrial Automation. Thank you very much, and I hope to see you next year again.
Thank you, and thank you for your attention. It was my pleasure.
So, ladies and gentlemen, we just finished our first OEM session by the VDMA. We had first Dr. Sascha Lange from PSIORI, CEO at PSIORI. Then we had Dr. Darius Soßdorf from MIC 4.0, and we finally had Bruno Adam from Omron industrial automation. It was a pleasure to be with you. If you have any questions, please contact our guests. They will be pleased to answer any kind of question you have and provide enough information. We'll meet again in one hour at the PSIORI session. I'm glad to be there with you again. So hopefully, and I'm looking forward to see you again. Bye-bye.